Let's talk about the fundamental theorem of calculus part 2 now. The fundamental theorem of calculus tells us when we have a continuous function and we're looking for the definite integral, that we can actually find the value of that definite integral by using an antiderivative. So it connects two really important.
Using the fundamental theorem of calculus part 2, evaluate a definite integral is a straightforward process. Step 1. We need to check that the function f of x that we are integrating is actually continuous on the interval defined by the limits of integration. Step 2. We need to find an antiderivative for f of x. We usually call this antiderivative big F of x. This means we're looking for a function whose derivative would be f of x. Step 3. We evaluate big F of x at the limits of integration. So we find big F of top and big F of bottom. Step 4. We take the numbers from step 3 and subtract. In other words, we evaluate big F of top minus big F of bottom.
Let's use the fundamental theorem of calculus part 2 to calculate the definite integral from 0 to 4 of x squared dx. First, we need to ask, is f of x equals x squared continuous on 0, 4? And the answer is yes. X squared is continuous on any interval. So now we use our rule to find the antiderivative. So x squared antiderivative would be 1 over 2 plus 1 x to the 2 plus 1. In other words, the antiderivative of x squared is 1/3 x cubed. So that's the big F of x that I want here is 1/3 x cubed. Now I'm going to take that big F of x and find f of top and f of bottom. And bottom here is 0 and top is 4. F top will be 1/3 times 4 cubed. F of bottom will be 1/3 times 0. Now I find the difference. What is f top minus f of bottom? I'm just going to get 1/3 4 cubed minus 1/3 0 cubed, which simplifies to 64 over 3. So if we just follow the 4 steps of this process, we get to the final answer. Let's see if we could find the definite integral from 0 to 4 of 3 over x to the pi dx. Again, our first step here is to ask f of x equals 3 over x to the pi continuous on the interval 0, 4. And the answer, it turns out here, is no. There's a problem when we try to plug in 0 into the function f of x. We have a divide by 0 problem. Because 0 to the pi is 0, it can't be in the denominator of our function. It's undefined. So the conclusion here, our conclusion is that we can't look, when we look at this definite integral, since this is not continuous on the interval 0, 4, and not use the fundamental theorem of calculus part 2. So what if we changed the interval? So what's the definite integral from 2 to 7.2 of 3 over x to the pi dx. So again, first we're going to ask if this function 3 over x to the pi is continuous on this interval. Here the answer is yes. This function 3 over x to the pi will be continuous on any interval that does not contain 0. This one, 2 to the 7.2, does not. So now let's find an antiderivative for 3 over x to the pi. It's important to rewrite this as f of x equals 3 times x to the negative pi. Then we can just apply power rule where we add 1 and bring it down. So 3 times 1 over negative pi plus 1 times x to the negative pi plus 1. And that just becomes 3 over negative pi plus 1 times x to the negative pi plus 1. All we're doing here, rewriting algebraically, and then applying basic power rule for antiderivative. And then we're using algebra one more time, clean up this 3 times 1 over negative pi plus 1. That gives us our final antiderivative. So now let's find f top and f bottom. Big F of x that we just found was 3 over negative pi plus 1 times x to the negative pi plus 1. The top is 7.2. All we're going to do is take that number and plug it into that function. We get f of 7.2, which is 3 over negative pi plus 1 times 7.2 to the negative pi plus 1. And the bottom is 2, so we get that the big F bottom is big F of 2. That's 3 over negative pi plus 1 times 2 to the negative pi plus 1. Now to find our answer, we just take the difference between the two numbers that we just found. So it's kind of a mess to say and kind of a mess to write. Not too bad because we're just combining the pieces that we had. This is going to be 3 over negative pi plus 1 times 7.2 to the negative pi plus 1 minus 3 over negative pi plus 1 times 2 to the negative pi plus 1. So this would be so you know our first question, f of x equals x3 plus squared continuous on negative 1 to 5. And the answer is yes, this is actually. The second is, what is an antiderivative of this x plus 3 squared? So if small f of x is x plus 3 squared, we're going to need to expand that out algebraically before we can do anything with it. So we can write this this is x squared plus 6x plus 9 when we expand the square. The antiderivative of this will just go piece by piece. So the antiderivative of x squared is 1/3 x cubed. The antiderivative of 6x is 6 over 2x squared. And an antiderivative of 9 is 9x. So this function turns out to be an antiderivative of small f of x. 1/3 x cubed, 6 over 2x squared plus 9x. Now I identify my bottom and my top, and I just plug those into the function. So here you see me doing that. And finally I subtract. So those two expressions that I just found. One thing that is important here is to be sure that you have these parentheses. When you go to subtract a whole block of something, it's really important that you put parentheses around whatever that block is. So this would be my final expression when I subtract my big F top minus my big F of bottom. So that's the fundamental theorem of calculus part 2.